and this is the VCM session for 11:15. I actually got some positive feedback about the last lecture, and so I'm trying to incorporate that as to, we go into this chapter. Well, tonight we will be going into chapter 12, and we started, Linda, with a little bit of review of some mathematical things, and we're going to continue that, and then we're going to go charging into chapter 12, and we're going to review a little bit of chapter 11 with an ultrasound example, then going into chapter 12, and and that's kind of the plan. All the accommodations are done, and so I'm sweeping them together and marking the papers and things like that. So we're going to be in good shape with that, and so that will be good. And everybody is in here for the ride now, and so let's focus to finish strong and get what we need to out of this course. So that's what Linda and I are committed to doing. And there's a couple other people have asked for special requests, and I am working on those, but I'm juggling a couple of things right now, but those are in play. And so, I'll be getting to those as I can. And looking ahead, I am going to get as much of a head start as I can on the any accommodations for the final. And I believe that our final exam is pretty much 1 month from today. I think we looked it up the last time, and it was on 12/13, and so we'll be doing that according to the COD policies that we looked up and shared last time. So we got 4 more weeks, and so just head down, finish strong, and make sure that you're prepared for the things we'll be doing. And again, it will be totally physics. Linda, is there anything that you would like to share with the group?
I think I'm all good. We are getting a couple people at the GSGs again, so just keep on coming, guys.
Okay, good. All right, so we have that, and I guess what I'm going to do is, and Linda, I am a co-host. So do you have to stop sharing for me to share, or?
Nope.
Okay, good. So what I'm going to do then is I'm going to, let's see, we're going to dive in, and I think I'm going to look backwards. And so I'm going to share some content, and I'm going to share my application screen. And I am going to be going to this problem right here. And so Linda, I think what you should be seeing is a page from the book. Is that what you're seeing?
I don't think you've started sharing yet.
I haven't. Okay, so I need to go back and start doing that because I was trying to do that. Okay, so I'm going back to okay, so I'm here, and all right, so I will go here. So I'm sharing now again. Okay, so it says I am sharing now.
Yeah, now I can see it.
All right, excellent, and I need to go and get it. Here it is, okay? And I'll make this a little bit bigger, and we'll talk about this example. But this is one of the things that we studied last time. I'm gonna make it a little bit bigger, I think. Yeah, there, it's a little bit bigger. And so this is an example, but this is an example of one of the fundamental things we studied last time, so this should seem somewhat familiar to you. But this is called ultrasound for medical imaging, okay? And and again, if this example probably is in the video, but I'm going over it in the VCM anyway as well. In this example, we'll look at the periodic motion of an ultrasound transducer. And again, the picture of the ultrasound transducer is down here. This is this gadget that this person is holding in their hand. And by the way, this is another thing that I've learned about ultrasound is you don't have to be left-handed to be an ultrasound person, but you're going to learn to use your left hand pretty well because most ultrasound people do it exactly this way. And you can see that this, and I don't know if that's a young woman or a young man. When I look at the hands, I'm thinking it might be a young woman, but we can't tell really, but they are holding the transducer, but you notice that they are holding it in their left hand, and that often is how it will happen. Okay, so we're going to look at the periodic motion of this, and we talked about what periodic motion was and so on and so forth. And so an ultrasound transducer, they'll say, is a kind of ultrasound loudspeaker used in medical diagnosis, and you guys are probably quite familiar with this. Now, the ultrasound is oscillating, and again, it's we have crystals in here is one of the physics ways we do it. And what happens is the electrical forces heat up the crystals. They begin vibrating very rapidly, and that's the vibration that goes into the patient's body and reflects off some. But anyway, the transducer in this case is oscillating at frequency of 6.7 megahertz. And again, you want to know that 6.7 megahertz is the same as 6.7 times 10 to the 6 hertz. And also by now you should know that a hertz is a cycle per second. And that will show up in units as a reciprocal second because cycles have no units often. So anyway, the question is, how much time does each oscillation take? And that means, as we're going here, so the oscillation is a cycle. And it'll also ask what is the angular frequency associated with this. So the calculation's not going to be too bad. We learned that this last time. We learned that the period, which is the time, is inversely proportional to the frequency, and we'll say more about that later tonight probably. So it's inversely proportional to the frequency, and to get the angular frequency, what we have to do is multiply that by that frequency that we find by 2 pi. So let's just wade into the problem then down here. And so the frequency is 6.7 times 10 to the 6 hertz, and that is 6.7 times 10 to the 6th, and that says s to the minus 1. Now that means 1 over s because the cycles really don't show up. And so hertz is radians per second or cycles per second. Now we know that, and we're not going to look up these equations, but you know, and this will be in your grace notes for the test, but you want to know that t, which is the period, is 1 over the frequency. So the time of a period for it to go from one peak to another, it's going to be 1 over, and this is 6.7 times 10 to the 6 hertz, but that's in the denominator. So everybody should be able to take their calculator and take 1 divided by 6.7 times 10 to the 6 hertz, and what you should get is 1.5 times 10 to the minus seconds. And I'd encourage you to do that. And what happens here is, and I could in fact ask you a question where I say, and give me your answer in microseconds. And so 1.5 times 10 to the minus 7th seconds is the same thing as, if I move this decimal point one place to the left, that's dividing by 10. To keep the number the same, I would have to multiply the other one by 10. And so I would have 0.15, and these is microseconds. And again, I could have said, give me your answer in microseconds, in which you would have to work towards this. So you see the period in this case then is 0.15 microseconds. Now, the angular frequency is the frequency that we started out with up here, but we're multiplying it by 2 pi. And you have 2 pi on your calculator. Actually, you have pi on your calculator, so you take 2 times pi on your calculator times f, and 2 pi is going to be 6.28 and change. So you're taking that times 6.7. Now, when you do that, you're taking 6 times something almost 7, you'll get a number that's very close to 42. So you have 42 times, and this is 10 to the 6. But again, if I move the decimal point one place to the left, I have to, that's dividing by 10, so I have to increase the decimal point on the other. So the way I would write this in radians per second, or in, and again, when we're talking about angular velocity, we're usually calling it radians per second instead of cycles per second. We will get 4.2 times 10 to the 7th radians per second. And so those are the equations that we have, and that's how we came about this. Are there questions out there on this? I'm going to count to 10 Mississippi to make sure that people are perhaps good with this. And Linda, if people come up in the comments and I don't see them because I'm sharing my screen,
I gotcha.
you can you know, keep me together on that. Okay, so I'm counting now. Okay, it sounds like there's no questions, and that's good, because we did talk about this quite a bit last time, so that's good. So now what we're going to do is, and I'm trying to figure out whether I want to go and talk about the logarithms or start talking about chapter 12. I think we're going to start talking about chapter 12, and then we'll go back and we'll talk about the logarithms as we have to. Now, these are things that we already covered. We talked about energy last time, and I think we really talked about all this stuff last time, and we talked about pressure as well. But now we're going to go into chapter 12 and do some more work, and we are going to encounter another fundamental thing in chapter 12, and chapter 12 is going to be dealing with mechanical waves and sound. Okay, so we're going to go and into the first section and talk more about that. Okay, all right, so I'm going to talk about some of these things, and I think there's some way that I probably could annotate this and highlight things, but I don't think I have that on this home computer, so we're kind of going to just run with it here. Let me think about something here. No, I'm not going to try to mix Blackboard with this. Okay, so anyway, a mechanical wave is every type of mechanical wave, as I said, is associated with some material or substance called the medium for that type of wave. So if you're talking about waves that are in a wave pool where you have water, the medium is water. If you're talking about sound waves, you do have to have a medium for sound waves, and sound will go through water, sound will go through metal, and sound will go just through the air. But it does require a medium. If you're in a vacuum, sound will not travel. So sound is an example of a mechanical wave. Now, there are some waves, and we'll talk a little bit about these, like electrical mechanic waves, that don't require a medium, and so they're not mechanical waves. But sound is a mechanical wave. Now, the speed of travel of a wave, if it is a mechanical wave, depends on the mechanical properties of the medium. And when you're doing ultrasound, often the medium you're going through is soft tissue in the body. Soft tissue is a lot like water. A lot of it is water, but it's a little bit denser than water. And if the motion of each particle is simple harmonic motion, the wave ends up being a trigonometric wave. And one example of a wave is shown with this picture. If you're just dropping things into a pool, it will form waves that will be going out like this. And later on tonight, I think we're going to get to and work a problem where we're actually talking about sound waves going out like this. But you see here, the waves are going out only on the surface of the water. If you're talking about a point source in space, the waves will be going out in, they'll be kind of like circles, but it's circles in all direction. And so there's going to be a spherical waveform that goes out, and we end up with a slightly different equation. But what you can see here is that the waves have crests and they have troughs. And here they're concentric circles. They're going to be concentric spheres in 3D when we're talking about sound. Okay, now here's some other words that are kind of useful. All right. So there are three kinds of mechanical waves that we can talk about, and we'll look at the picture of them. And we're just going to envision that the medium is a stretched rope. That helps us think about these. But what we have is a pulse that can travel down the length of the rope. And so I'm going to pull down just a little bit, and we'll see here. So there's a person grabbing a hold of the left end of this in part A, and they're giving this rope a shake. And notice that the rope itself, even though it's, you can kind of say, hey, the bump or the wave is moving. What happens is the particles of the rope are only going up and down. They're not moving to the right, but the velocity of the wave is moving to the right. Now, this is called transverse wave. And a transverse wave is when the velocity is perpendicular to the motion. So you see these hunks of rope are going up and down, but the velocity is going to the right. So if you think about up and down being up and down and the one going to the right, you say, oh, that's a 90-degree angle. Okay, so what it says in the blue there, the particles of rope are going up and down. So as the wave passes, each particle of the rope moves up and down transversely. That means that the motion of the rope is perpendicular to the velocity of the wave. So you see what's really happening is there is energy that's being transferred down this wave, and that's what's causing the things to go up and down, and that's going to be harmonic motion. So we have a case here where we can have transverse motion of the wave itself. Now in part B, we talk about longitudinal motion, and what really happens is that sound is a longitudinal wave. And I mention that because that kind of thing is actually on your certification exams. They will say, what kind of a wave is sound? And one of the answers might be transverse, and another one will be longitudinal. Well, in this case, and in sound, it really is longitudinal, because if Linda were to speak, as she, sometimes might, there is energy comes out of her voice and strikes these molecules and starts shoving the molecules. Now, the molecules are like the particles of this fluid. They're going to bounce back and forth, transferring energy, and the energy gets transferred along this way. And you might say, well, gee, how come whenever I see an oscilloscope, it looks like it's a sine wave? Well, that is because often microphones will not sense the actual wave itself, but they'll sense the pressure. So what happens is, as these particles are shoved together, and we call this refraction and compression and refraction, when they bounce back and forth, what happens is they undergo changes in pressure. And it is the changes in pressure that are measured with microphones. And so what we can see is that the pressure will increase and decrease. So what I'm saying is that often, even though it is a longitudinal wave, a microphone will actually be showing it, or an oscilloscope will be showing it as a transverse wave. And then you can have even more complicated waves that actually have both transverse and longitudinal components, and that's pretty complicated. If I go down here, there is the definition of a longitudinal wave. If the particles of the medium move back and forth parallel to the wave's direction of motion or direction of travel, we call this a longitudinal wave. And sound waves are longitudinal waves because these waves hit your ear, and that causes things to happen. And we'll talk a little bit about sound waves, but realize that sound waves can be carried by other liquids such as water and solid objects such as walls. And so we have longitudinal and transverse displacement. And all waves have a common characteristic. There's an equilibrium state, and then they go up and down or to the right and left. And as it says down here in bold, waves transport energy, not matter, from one region to the other. And we talk about the disturbance or the transfer or transport of energy is called wave propagation, and the speed that it moves along is called the wave speed. And here's an example of, they can give a 2-minute warning if there's a bad storm, and they've gotten pretty better at this. And so you can, seek shelter if you have like an earthquake coming, or in the Midwest, although actually there are serious fault lines in the Midwest, and someday we may have an earthquake in the Midwest. And in fact, we do sometimes have earthquakes in the Midwest. We have more tornadoes than we have earthquakes. But again, you'll find that what really is happening is that tornadoes are energy being transferred from one place to another, and so we have that. Okay, so let's start looking a little bit more about periodic mechanical waves. And I went too far, too fast. And so we'll go back up to the top of this again. And we're approaching another major equation like we had last time. And you remember last time the big equation was that T is equal to 1 over F. And we have a similar thing about angular frequencies. But now we're going to talk about periodic mechanical waves. And so down here near the bottom of this page, you say, as usual, F is equal to 1 over T. But when we get more and more of those, here's a nice picture talking about what's happening. And you notice that over here, we have a spring and a mass. When I say over here, I'm talking about on the left-hand side. And we have this, we're pushing in, and the spring pushes back and forth out. But we have a rope tied to this. And so what happens is this spring going up and down is actually shaping the rope going up and down as well. And so you see that we have crests and we have troughs, and we have amplitude, which is the distance from the equilibrium point to the maximum or the minimum. And you have the crests and troughs, but it moves along that way. And this is simple harmonic motion. Just to read the words then, the simple harmonic motion of the spring and mass generate a sinusoidal wave in the rope. Each particle in the rope exhibits the same harmonic motion as the spring mass. It's going up and down, but the amplitude of the wave is the amplitude of this motion. That's how far does it go up and down. So what we get is we can see that that wave is going along, and we want to know about amplitudes and being able to generate those and things like that. And you can see here that these particles of rope really just go up and down. They don't really move. Now we come across a thing though that is called and this is a new term for some of you, it's called the wavelength. Okay, so I'm reading here in this paragraph that's near the bottom of your screen. For a periodic wave, the length of one complete wave pattern is the distance between any 2 points at corresponding positions on successive repetitions of the wave shape. And let's, in fact, go up here and look at that picture. So you see, here I am at a trough, and I'm in the middle, and I don't think you can see my, you can't see my little pointy thing, can you, Linda?
I can see your cursor, yes.
Wow, okay, that's like really special. Okay, good. Okay, so you see a wavelength is from, and I'll show you a couple of wavelengths here. A wavelength could be from the top of this to the top of this, or from just short of the top to just short of the top. Down here, for example, a wavelength goes from here where I'm at the 0 point, and then I go until I've done one complete cycle, and that is a wavelength. And they're showing a wavelength down here. So each wave advances by one wavelength, and the Greek letter that we often use for wavelength is this Greek letter. It corresponds to a Greek L, and it's called lambda. And so lambda is how far the wave moves. Now that is going to be a distance. So it'll be meters or millimeters or centimeters or nanometers. But each wavelength advances by each wave advances by one wavelength during each period t. So you see, we not only have frequencies, but now we have periods and we have wavelengths. And each point moves up and down in place, and particles one wavelength apart move in phase with one another. That means they're moving just like the other one is doing. Okay, so we call this the wavelength of the wave, denoted by lambda. And the wave travels with constant speed v and advances a distance of one wavelength in a period of time t. So we can relate these as follows. And this, of course, is an important equation for you. And it's down here. It's shown as, I guess, it's called equation 12.1, it looks like. But this is that, and I have asked problems on the final exam dealing with physics that are no more complicated than remembering this formula. And this is that V, velocity, is equal to lambda times frequency. And since frequency is 1 over t, V is also equal to lambda divided by t. And here the units are, V is in meters per second, F is in hertz. And remember, hertz is 1 over a second, or cycles per second, and lambda is in millimeters. So this is another really important equation for you to memorize. And we're going to talk about problems that we can solve using just this equation. And Linda, it's kind of quiet out there, and I'm every so often going to pause just to see if there's any questions. But if I drop off, you can, send me.
Amber does have a question.
Hey, all right, good. Way to go, Amber.
Hi. You said you would ask questions about, well, you have in the past asked questions about the formula. If we were to answer the formula, how would we put the Greek letters on the computer?
That's not the way I will ask the question.
Okay.
Okay. And so I'm going to show you that, but I might ask you about wavelength. In fact, we're going to do this, and tell you what, Amber, I will address your question pretty briskly, I guess, in just a moment. I'm going to read these notes though. And then we're going to do an example of this, okay? And you don't have to be able to do the Greek letters. And I can do Greek letters, and so can Linda, but it actually takes quite a bit of energy to do that. And so I'm not asking you guys to do that. It's mostly mental energy. It's not so much kinetic energy. Anyway, here's the notes. So Amber, I think your question will get answered pretty soon. Now this equation, this V equal lambda times F, is true for any wave, including those that are not mechanical. In fact, we're going to look at light waves in some examples, and we're going to see that, oh yeah, this is the equation that we have going. So so this is true for any wave, including those that are not mechanical. And for many waves, V is determined by properties of the medium. And that's another thing that they will ask you on your certification exam. They'll say, hey, if we change this, what can we change? So you do have to think about the medium, and the medium is usually soft tissue that you're dealing with, but what is determined by that? And the speed is different. The speed of sound, in this case, is going to be different depending on your medium. And so it says for many waves. That's not true about light, but it is true about, actually it's sort of true about light too. We'll say more about that. But it's property of a medium. And so in such cases, if the wavelength changes, then the frequency must also change to keep the product of the two, that is lambda times F, a constant. Okay, so I'm going to ask you to keep that together. And Linda, this is a little bit of an experiment. Now, Linda, I think we can just share on top of each other, can't we?
I think you should be able to.
Okay, now, but what I was talking about was not I should be able to, but you and I together should be able to.
Oh, no, both of us can't share at the same time.
Okay, so now here's what I'm going to do, Linda, but I want to be as clear as I can when I stop sharing, okay? And Linda, I know you have that PowerPoint and you have it showing in a slideshow mode, or you did. I'm going to stop sharing, but I'm going to want you to go to a problem, and so you might have to advance the slides a bit. And the problem I want you to go to is called 12.1. Okay. Am I making sense, Linda, or am I not
Yeah, no, I'm just
communicating
trying
well?
to find it right now.
Okay, so she's looking, and Linda, I'm going to stop sharing,
Okay.
and I can help you find it if you need. Oh, and Linda,
I see
here's the other thing.
12.2. I don't see a 12.1.
Okay, well, maybe I didn't do a 12.1, which is a little bit disappointing. Let me try to find another one that's maybe better. Do you have a 12.3?
Yes, I do.
Okay, now, and Linda, and I know I'm giving you a lot of direction here because I was juggling a couple things and I kind of prepared but didn't completely prepare this. Can I ask you to cut out 12.3 and make it big on a different slide perhaps, and show us the slide that just has 12.3 on it? And am I being clear again, or not so much?
So you want me to just share the image of it?
I want you to snip out 12.3. I want it so the students can see it, and I think it's really tiny the way I pasted it into the slideshow.
No, I think it's pretty big.
Oh, all right, good
if
enough.
you open up Collaborate, like I can read it, and my eyesight's
Okay,
terrible.
okay, so I'm stopping. In fact, I have stopped sharing, and so now you should be able to share.
Yeah, I already have it up.
Okay, and I'm on the wrong page or something. Hold on. I need to look at, yes, there we are. Oh, no, Linda. Now, Linda, I can move this slide, so, right? Now I'm going to go back and show you
Yes,
what
you
I
can.
really meant, I really meant this problem is called 12.1 right here.
Okay, so just number 1 on this slide.
Yeah, and I'm sorry, I wasn't looking at. That's what I want is this one. Okay.
Gotcha.
All right.
Let's see what I can do.
And if that's big enough for students to see, and actually they do have it there. Okay. So we're going to do a little bit with this. And Amber, this is an example of, now don't say, oh, this is exactly what he's going to ask, because that would be a lie. But this is getting at those things. So this is a biological thing. And what this is saying is that audible wavelengths. Now, by the way, audible means you can hear it. And one thing that you guys can't do, and it's nothing wrong with you, but you cannot generally hear ultrasound because your ears, wonderful as they are, cannot hear megahertz sounds, but you can hear, in fact, I'll read this then. The range of audible frequencies is from about 20 hertz to 20,000 hertz. Now that could be 20 hertz to, and you could say 20 kilohertz. That would mean the same thing. Okay. But then the question asks, what is the range of the wavelengths of audible sound in the air? Okay. So we want to know what's the wavelength. And Linda, do you have a calculator nearby?
Yes, I do.
Okay, so Linda, we're going to go and do this part A, and I think we're going to do B. We're going to do a handful of these things along the way. But I think, Amber, at the end of this, and Amber, not to embarrass you, but I might check back and say, do you understand what I was saying about that? Because in your head, you're going to be thinking about lambdas, but you're not going to be writing any lambdas. Okay, so this is 20 hertz to 20 kilohertz. So Linda, you have to stop sharing. So Linda is stopping sharing, and I am going to then begin sharing, and I'm going to a whiteboard. But Linda, you're going to maybe do some things in the calculator and tell me numbers or something as we go to this. And then we're just going to be bouncing back and forth here, and we're going to be doing a handful of these problems. Okay, so I need to get something to write with up here, and I am getting something that is black, I guess. So I'm going to do this. Okay, so now we know that F is equal to, and in fact, remember what we said. We said the equation that we know is that V equal F lambda. So that means that lambda, okay, so the frequencies go from, on the low end, it's 20 hertz. And I will call that F low for FL. That's the lower frequency, and the high frequency that people can hear. And by the way, if your hearing isn't great, and when people get older, they actually don't hear even in, don't hear this complete range. And this is 20 kilohertz. And I think I said last time, but it's true. Sometimes speaker magazines and things like that will say, oh, we have a frequency response of 28 kilohertz. Nobody can hear that last 8 kilohertz. And so you're spending a lot of money for things that you can't hear, but that doesn't stop people from buying it. Anyway, so we have this going on. But then the question was, what wavelength is down here? So what corresponds to this wavelength, and what corresponds to this wavelength? Now, Linda knows the answer to this, and I'm putting these things here, but what we're going to find when we do this, that we're going to find that that these are that if F is lower, the wavelength is going to be higher. And if F is higher, the wavelength is going to be lower, and we call that inversely proportion. And Linda, we need one more fact for students to do this. It said that this was in air. So you see, this is not an ultrasound study, this is air. So in air, a fact that we know, and I suppose there'll be grace notes for this or something, but a fact that we should know is that the velocity of sound in air, and it does depend on the units, and it depends on other things, but temperature even a little bit, not a lot, but a little bit. But the number that we're going to use is the speed of sound in air at I'll just say room temperature is 344 meters per second. So you see, we're talking about sound, and we're saying that humans can hear, and your dog can hear differently. Your dog can hear higher frequencies than you do. Sometimes you may know that dog trainers will use a whistle that that they'll blow on, but the people watching the dogs perform or something like that can't hear it, but the dogs can, because dogs have different ears than you do. But anyway, so we have the so we're supposed to say, what's the range of wavelengths? But you see, this is a sound wave, so we know that the velocity of sound is equal to 344 meters per second. So what's going to happen then is we're going to have lambda, and you remember that the equation was this: V is equal to lambda times F. And again, even though I give you guys grace notes, I really wouldn't have to give you grace notes, because you ought to be able to figure this out. Because you see, velocity is meters per second. Well, wavelength comes in meters, and frequency comes in reciprocal seconds, so that would be meters per second. So that's a good way to maybe memorize that formula. But lambda then is going to be, if I use algebra to solve this for lambda, lambda is going to be equal to, I would divide both sides of that equation that I just wrote by F, and I would say lambda is V over F. Now you see, we're talking about this is in air, and the sound is going through air. So you see over here, I will have 20 hertz. That's 20 reciprocal seconds. Actually, I need to erase this because I'm doing this the wrong way. So I'm going to erase this. So you see lambda, I should do that down here. So I'm going to do that down here again, bear with me. So I'll get my pencil again, I am down here. So this means that lambda, which is what we're solving for, is equal to V over F. So up here, what I'm going to have is 344, which is V, and this is meters per second. And this is going to be divided by the frequency, which is 20 hertz. Now it's useful to know that hertz really is 1 over seconds. And so the seconds are going to whack with one another, and we're going to have meters as our unit there. And over here, we would have the same story, except, and you see I still would have 344. This is meters per second. And then down here, what I'm going to have is, now I have 20 kilohertz. So that says this is 20 times 10 cubed. And this is going to be 1 over seconds. So I'm going to get some meters out of all of that. Okay. Now, what I'd like for everybody to do is pound that into their calculator, and that includes perhaps Linda doing that. And Linda, tell us what you get for the left-hand wavelength over. Well, let's give everybody a count of 5 Mississippi to do that. So you pound that into your calculator, and your units are going to be meter. And so, Linda, what do you get on this left side? And I'll write down what Linda says. I know the units are going to be meters.
That would be 17.2.
Now, you might not know that, but that's actually kind of a long wavelength. That's more than 50 feet is the wavelength. So that's a very long wavelength. But the reason that's a long wavelength is because the frequency is tiny. Okay, but Linda, do the other one, the high one there. And I don't know what Linda actually will do when she will do that. She might give that in some kind of units. In fact, well, okay, so Linda, let's start with just what number do you get on the other side? And the other side is this piece over here on the right-hand side. What number do you get here?
So that would be 0.0172 meters.
0.0172 meters. Okay, and see, she took into account the fact that you have this 10 to the minus 3, so you were moved over that way. And if we were to call this, I don't know, we could call this millimeters or something like that. And in fact, I'm glancing at my notes to see how I wrote it. I wrote it as 1.7 centimeters. And I could also, Amber, and again, Amber, I'm not trying to pick on you, I'm trying to answer your question. I could say, hey, what is the wavelength? And give your answer in centimeters or something, and you would do that. But you see that there is an inverse relationship that exists between the two of these, because if lambda is big, F is small, and if F is big, lambda is small, and we call that an inverse relationship. So Amber, I'm going to pause and just so you see, you had to recognize lambda, I guess, in this, but you didn't have to ever write a lambda to answer the question I was giving.
I got it. Thank you.
All right, excellent. Thank you, Amber. Okay, now I was sharing, so I'm going to, how do I stop sharing on this screen? Linda stopped me from, I don't know if I did that or Linda did this, but I'm not sharing now, I guess. And so Linda, now can you share?
Yeah, you want the PowerPoint back?
Yeah.
Okay, sounds good.
But we're going to, but we're now going to do part B in this first one. Now there's a whole bunch of problems here, but we're going to use part B for this. And this is visible light, okay? Now this is a big difference though. I'm going to ask everybody to do this and then we'll do it together, okay? But the range of visible light. Now you see your eyes are a remarkable thing too, and you can see visible light, but I'll also tell you that there's light that you can't see. Like you can't see X-rays, and you can't see microwaves and things like that. So you see there are ranges when you can do it, but here's the range of visible light. It extends from 400, and that says nanometers. And again, you guys are supposed to know what those units mean. So 400 nanometers to 700 nanometers, that's what your eye can see. So what is the range of visible frequencies of light? Okay, so I'm going to ask everybody to do this. Now, the fundamental equation that we have is the same as what we've talked about before, and that is that velocity is equal to the product of lambda and F. And that's always true. But you remember on the other problem, I had to give you the velocity of sound in the medium, well, I'm going to say that this is the velocity of light. And I think I'm looking at my notes to make sure what I did. This is the velocity of light in a vacuum. So I'm telling you what the velocity of light is. Now you have to be able to use these powers of 10 to deal with this. And so, and I'm asking you to work this problem now. And so what we're going to do is we're going to be talking about that the velocity of light actually is a constant, and the velocity of light in a vacuum is 3.00 times 10 to the 8th meters per second. Now that's really fast. Light does really go fast because that's going really fast, but that's what it is. And the velocity of light is often shown as we often use the word, or not the word, the letter C to stand for this. So everybody give this a go. And Linda, how long do you think it would take people to do this? Because we want to find the range just similar to what we did before.
We'll give them like 5 minutes.
Okay, so we're giving them 5 minutes to do this. And Linda, I'm going to ask you to kind of declare when 5 minutes are up, and then I'll start sharing again, and we'll work through this and see if they get a good answer. But Amber, and again, Amber, I really apologize for always calling on you, but you were courageous enough to ask a question. This is a little bit of a test because, and again, it's not a test anybody has to be anxious about, but this is testing, do you understand how to do this kind of a problem? So everybody do this, and Linda's watching for 5 minutes then. And then Linda, let me know when 5 minutes has expired because you're going to be the timekeeper. And then I think we might do maybe, we'll talk about 2 other problems, but we won't work them, but we'll work these 2. So everybody is using this fundamental equation for this one. Go ahead, please. And Linda, just shout out when we're good to go with this.
Will do. They've got about a minute left.
Okay, thank you.
All right, they should be good to go.
Okay, excellent. All right, so let's just go through and work this, and we can compare notes. And Linda, and let's just say, okay, so let's see. Now, the range of visible light extends from 400 nanometers to 700 nanometers. Now, the reason Linda knows those are wavelengths, and it didn't say those are wavelengths, but the reason Linda knows those are wavelengths is those are meters. So that's good. And the other one, we're talking about frequencies. So, and I told you what the speed of that was. So I'm going to, and I think that maybe means Linda has to stop sharing. I don't know how this actually works. I'm going to share a blank thing here, a whiteboard. And Linda told me how to erase this, that there was something up here that maybe the eraser does it all. Let me figure out, where's the eraser? It is over here.
So it's right next to the stop sharing button on the top right-hand corner. It's got like
Stop
a
share.
whiteboard with a trash can on it.
Okay. Now that actually didn't. Okay, so there's a trash. Oh, yes, found the trash can. Yes, there we go. Clear annotations. Yes. There we go. Thank you, Linda, again. I'll remember that one day. Maybe even again today I will remember it. Okay, so we are here. And so again, the fundamental equation is that the velocity is equal to, I guess we're looking at blue, is lambda times the frequency. But when I plug in numbers here, then I know the speed of light is 3.0 times 10 to the 8th, and that is meters per second. And I knew the wavelength was this, so I wanted to know what the frequency. So I'm going to have to divide this by the wavelength, and one of those wavelengths was 400 nanometers, and so 400 nanometers here, and nanometers is times 10 to the, let's see, 400 nanometers, so that's going to be times 10 to the minus 9. Okay, and so what you can see is, and Linda, if you'll pound that into a calculator, and again, this was let's see, that was the this was the wavelength, so this was meters, and you see what happens is the meters are going to cancel, so the answer is going to be reciprocal seconds, so the answer is going to be hertz. Now, so, and Linda, we're going to do this in hertz, so we're not going to megahertz or anything like that. And so she's just pounding that in her calculator, and tell me what you get. And tell me in a power of 10, though, maybe.
All right,
Maybe
I'm getting 7.5 times 10 to the 14th power.
Okay. And again, this doesn't surprise you because you see the wavelength was tiny. That means that the frequency is a big number, and this was, I'm going to put plus up here, was 10 to the plus 14, which is a big old number. And in fact, this is a frequency that totally dwarfs your ultrasound frequencies. You're not doing this. And I could have asked you to give me the answer in megahertz or something like that. And Linda, if you do the same thing, again, the velocity is going to be the same, but if you use 700 nanometers, what do you get? Because we were trying to find the range here.
That is about 4.28 and times 10 to the 14th.
Yep, 10 to the 14th again. Okay, so you see this is where you go. Now, you might look at this and say, damn, you really don't have a significant, Seven's getting excited about this problem, I think. You might look at that and you might say, boy, there's not much distance between these ranges, but this is an enormous distance because the distance between them is 3 times 10 to the 14th. That's an enormous gap because when you subtract these two things, you're subtracting, you're going to get 3.3 times 10 to the 14th, which is an enormous number. Okay, now what we're going to do now is we're going to do something quite dramatic, but it's a big step because we're going to start talking about attenuation. So Linda, I was sharing this, so I'm going to still stay sharing my screen, but I'm going to show you a different application screen. And I am going back to not the PowerPoint, but I'm going back to the book. And so here was a fundamental equation. And I'm not talking about every fundamental equation, but we're talking about some of them. And the next chapter talks about wave speeds and things like that. And again, all this stuff is good and important, and a lot of the stuff is in the videos. But I'm jumping all the way to, and we're going to spend the balance of the discussion time today talking about this. And it's going to be called Sound and Hearing. Okay, so I'm going to read a little bit, but then we're going to go directly to some things. Okay, sound can travel in gases such as air, liquid such as water, and solid materials. And soft tissue is a mixture of water and a little bit of tissue. And so the simplest sound waves do have frequencies, amplitudes, and wavelengths. And the ear is sensitive to wave frequencies from 20 to 20,000 hertz. We've already said that. But we also use the term sound for similar waves with frequencies above what you can hear. By the way, this is something that is on your certification exams too. They say ultrasound, what is it? And it's above 20,000 hertz. And it's infrasonic if it's below the range of human hearing. So sound waves also can be described in terms of variations of pressure, and we talked about that. That's what microphones do, and things like that. And microphones and similar devices usually sense pressure variations, not displacements. Okay, and by the way, there's a lot of really good stuff here. It talks about how wonderful your ear is, things like that. But I want to move ahead and talk about intensity. Okay. Now, let's talk about what intensity of it is. And intensity is a new measurement for us. And so, and it transfers energy. So we define the intensity of a wave, and I'm just calling that like I. So I is the time averaged rate at which energy is transported by the wave per unit area. So you see, this is power, which is the change in energy per unit area. So it's the rate at which energy is transferred by the wave per unit area. So you see, this is the rate of energy changing is called power. So intensity is the average power per unit area. And the unit of power, you will recall, that's a joule per square meter, but that's called a watt. So the intensity is of the faintest sound wave that can be heard by a person with normal hearing is 10 to the minus 12 watts per square meter. Now that's a very, very, very small number. And so that is, that's watts per square meter. Or it shows here 10 to the minus 16 watts per square centimeter. But please understand that we've introduced a whole new unit now, and we're talking about intensity. All right, and it goes on and talks about things, and there's examples here, and you know, I go over those in the videos. But here is an important equation that's kind of in the center of your page, and this is going to be something that you're going to be using. So this is an important equation for intensity. And this is going to, so intensity is equal to, that P stands for not pressure, but that P stands for power. So intensity is the power divided by the area. But this is the surface area of a sphere. So you kind of want, and actually this is one thing that, you know, I do a better job of this, I think, in the classroom. But what I would do in the classroom is I would hold up my index finger and I would say, okay, I have a source of power at the tip of my index finger, and it's sending out sound waves. Well, these waves are going to go out spherically, and Linda knows that the equation of the surface area of a sphere, now that's not the volume of a sphere, that's the equation of the surface area of the sphere, is going to be 4 pi times r squared. And so this is an equation you need to know. So this, and let's see, the average intensity through a sphere, let's see, where is this? For such a source, okay, let's see, I'm going up here somewhere. Oh yeah, the simplest source of sound is a point source that emits its power uniformly in all directions. So it's radiating not like those drops of water, but it's going out in a spherical fashion. So for such a source, the intensity I is equal to the power divided by, and this is inversely proportional to r squared, but the actual formula is it's P over r squared. So that means if we have I1 and I2, who are different intensities, then I1 over I2 would be, the ratio would be, if you were to do the ratio, you would have R2 squared over R1 squared. So it's inversely proportional to R squared. So, and this is a very important equation that we're going to be talking about. So, you know, hang on to this equation, and we're going to be doing some things with it. Probably next time, because I do watch the clock carefully, and we're blessed to have Linda with us the entire period tonight. But we're getting closer to the end. So that's an important thing, so make sure you make note of that. But now we're going to start talking about some other thing, and this is, again, another thing I'm supposed to teach you, and this is called decibels. Okay, and deci means this is base 10, and it turns out it's named after Alexander Graham Bell, and I used to work for companies that were called Bell. They had bells in their name because they were companies that can trace their heritage back to Alexander Graham Bell. And in fact, as a telephone engineer, I in fact talked about decibels. Cable TV engineers talk about decibels, and ultrasound people talk about decibels because these are measures of intensities, but they're relative measures of intensities. So this is kind of something that is a little bit different than what you've run into before, and we'll talk about some now, and we'll talk about a lot next time. Okay, because the ear is sensitive over a broad range of intensities, a logarithmic intensity scale is usually used. So that means that yes, there are logs in this equation. And one blessing is you don't have to worry about a whole bunch of logs as long as you're using log base 10, which is the common log, and that's the one we're using here. But this is the definition for the intensity level or sound level of a sound wave. And the sound wave is called beta. And Amber, you see you're getting exposed to all these Greek letters, okay? But that's just the way physics is. That's the way math is too. Math has their own letters that they feature. Linda could talk to you someday about epsilons and deltas, but probably not today. Okay, so the sound level beta of a sound wave is defined by this. So beta is equal to, and there's a 10 there, and 10 is a number, but 10 is also a unit because the sound level comes in units that are called lowercase d, uppercase b, and that's the way you say when you run across that. You call that decibels. Okay, so this is decibels. And so in this equation, and so this is the equation, beta is equal to 10, and they put the dB in the middle. And to tell you the truth, that I don't like that so much, but that's what physicists do. And mathematicians probably would put it at the end of there. But anyway, dB is the unit. So that's 10, which is a number. And that's a ratio of the logarithm. And this is the logarithm base 10. And the numerator is the intensity that we want to be talking about. So we're measuring what is the level of that intensity. But we're saying relative to a reference intensity that is called I0. So in this equation, I0 is a reference intensity, and this is chosen to be, so in the problems that you work, it will always be this. It is 10 to the minus 12 watts, that's power per square meter. And the log here denotes the logarithm to the base 10, not the natural logarithm. Now you might say, why do I care about that? That makes a difference in where you punch your calculator button. And next time, maybe early in the period, we'll talk a little bit more about logarithms, and maybe I'll show Linda what buttons to punch on your calculator. But the units are decibels, abbreviated dB. And so those are intensity levels that you have. And this is something that you're supposed to know about. And in fact, there are questions that they ask on your certification exam about decibels, okay? And so here's a table, and I do know what time it is. We're almost finished. But here are sound levels. So the threshold of hearing, you can see at the very bottom of this, has a level of 0 because that means that it is 10 to the minus 12. So you see the threshold of human hearing is what you have down there, and you have all of these things that go up, and the threshold of pain, which is what fire alarms would be using, are 120 dBs, because when you hear a fire alarm, you say, I want to get as far away from this fire alarm as I can, as fast as I can. Okay, Linda, anything for the good of the order? I'm really ready to dismiss them unless you have something to say.
No, I think we're good.
Okay, now this gets a little bit deep. Linda, I know, has worked with students before on this, and I got to tell you that this logarithm thing is something some students struggle a bit with. So make sure you stay engaged here as we go into this next lecture. And so Linda will turn this off and turn the recording off, and I will upload it after it's rendered, and we'll go from there. Time is precious. Each day must count. Do the math. It'll make you strong. Maybe I'll see some of you in my office hours, or maybe not. I don't know. Take care. Good night.